Hello, I'm Mike McCulloch. Today I'd like to talk about QI and cold fusion. So cold fusion is a phenomenon that is now called LENR, or low energy nuclear reactions, that was first noticed by Pons and Fleischmann back in 1989, and they caused a lot of controversy with it. So what they did was they electrolyzed heavy water with a palladium cathode. So heavy water being deuterium, heavy hydrogen. And they found that after a while, more heat was being given off than could be explained by chemical processes. And also some helium-4 was given off as well. But there were no gamma rays or neutrons emitted, which made everybody suspect it wasn't a real effect, and it was very difficult to reproduce. So eventually the furore died down. But over the years, several experimenters, quite a few in Japan, have managed to reproduce these results. So it does seem to be a real thing. So when I read about this, I read about it in papers by people like Ed Storms and Russ George, and it was a very interesting subject, and I wondered if quantized inertia could explain it. So quantized inertia depends very much on Heisenberg's uncertainty principle, which is delta p times delta x is greater than h bar of 2. So the uncertainty in momentum times the uncertainty in an object's position always has to be greater than a particular very small number. Now, the new part of quantized inertia is to say that dx is determined by a horizon. So if an object has a very close horizon, a limit beyond which it can't see, then its momentum should increase. And if you apply this principle to inertial mass and use a Rindler horizon, then this predicts inertia in such a way that predicts galaxies without dark matter and all that kind of thing. So how does this apply to cold fusion? Well, okay, so consider a cavity. This will limit the uncertainty in position, dx, to the size of the cavity. What this means is that objects within the cavity will have to accelerate very rapidly in order to see UNRWA radiation short enough to fit within the cavity. So that means you'll have a lot of very hot particles in there produced by Heisenberg's uncertainty principle, if we accept that the metal is producing a horizon. So if you have a very small cavity, the temperature should be very high. Now, the normal problem cold fusion theories have is making deuterium's atoms stick together. Usually they're repelled electrostatically from each other. You have to drive them together, and usually this can only occur in the sun, for example, which has enough heat to give the particles enough speed to smash into each other, or in very large magnetic fields. But if quantized inertia is able to produce very hot temperatures in very small cavities, then this would be like a tiny sun. So it would mean that there's a lot of radiation pushing the deuterium nuclei together, and in fact there would be a sheltered region between the two atoms without UNRWA radiation, and there will be UNRWA radiation outside them pushing them together, so they will tend to push together more rapidly than usual. And this could account for the fact that these deuterium nuclei are somehow fusing together in the palladium. So I calculated the size of cavity you would need by quantized inertia to produce the temperature needed to fuse the deuterium together, and it turns out to be 28 nanometers. And this isn't so bad as an estimate, because palladium is thought to have cavities of that size in it. There have been some reports about that anyway. So it could be that quantized inertia explains the origin of cold fusion, and all we have to do to get energy in this way is to build palladium cathodes for the electrolysis that have very tiny holes in them. Okay, so I hope you've enjoyed this short, and I look forward to seeing you next time. Goodbye.